So, the neutral ground, identity, and the concept of an inverse. It is very important, guys. So, the very first one, the identity matrix. As we all know, the identity matrix means I do have the square matrix that all of the numbers on diagonals are going to be 1 rather than other kind part that are going to be 0. So, the identity matrix I is a matrix equivalent of the number 1. So, multiplying any matrix by I leaves going to A as unchanged. It means that I times A is equals to A. Imagine that A is 3 by 3. So I should also be 3 by 3. So I do have 1, 0. So I would like to prove that times this one is actually going to be the same value. So I do have A, right? I do have this kind of I. And again, just before that, I checked this, some kind of rule, and I know we can do this multiplication. So let's do that. First row, first column, second column, third column. First row by 1, 0, 0. What would happen? 1. First row by second column, what would happen? 8. First row by the final one, I do have 7. Do the same thing over here. 2, 5, 9. The second row, first column, second column, third column. If you do that, you still have 2, 5, 9. Do this last part, you still have this one, and it means that nothing has changed. What is the inverse matrix that we show it as a to the power negative 1? It's somehow like this. You remember that we had f of x is equals to y, and sometimes we are looking for f of negative x, of f inverse of x. For the square matrix, this is very important. We are talking about the square matrix. What was the square matrix? Square matrix was the one that the number of the dimension means that the number of columns and rows are the same. And its inverse, or a to the power negative 1, is going to be another matrix that when multiplied by a yields the identity matrix. It's the equivalent of division. What does that mean? It means that if I do have the matrix as A, and if I do found another matrix, for example B, and the solution is going to be I can know that B is going to be A inverse. How are we using that? For division. How are we going to use that? In an equation, and I will show you how. The very first way we have to see is that matrix of A times the matrix of inverse of this one is going to be identical. So important note, not all the square matrices have an inverse. This is very important section, guys. It doesn't mean that whenever you just find your square matrix, whatever is that, you can find inverse. No, you cannot do that. I will tell you how you can find it and understand that it does have a matrix or there's some kind of inverse or not. But a matrix that has an inverse that is called invertible or non-singular. We need a tool in order to determine if an inverse actually exists. How we can do that? By something that we call it as determinant. A single number that reveals the matrix story. This one is a very important section about the matrix. You're going to see that a lot. You're going to use that a lot. First of all, what is this guy is going to tell to us? This guy is going to tell us that if you find the determinant of a square matrix, right now we don't know how we can solve it, but imagine that there is a number there. If determinant of A is something that is not equal to 1, negative 2, 10, 20, 12, whatever, the matrix A is invertible. It means that I can find and something that I can multiply by A and I still have the identity. And the system x equals to b has a unique solution. What is x equals to b? It's the equation related to matrices. I will talk about it. Geometric meaning. It means that the absolute value of the determinant is a scaling factor of the area of 2 by 2 or volume of 3 by 3. When a space is transformed by the matrix, okay? Whatever number that you found is going to show you that if you use that specific matrix, you are going to have scaling. And how you can find this scaling? By use the determinant. It's going to give you an answer that in each dimension that how much scaling you have. A negative sign indicates an orientation flip. Rather than just scaling on the positive, we do have scaling on the negative itself. So the very first one is that how we can calculate that. Determinant of A, B, and C and D is going to be A times D and B subtracted by B times C. It's somehow like the one that we do have about the multiplication. The one that we do have related to the fraction itself. So it's going to be A times B and subtracted by B times C. So we are going to have a number like this. This is for just 2 by 2 itself. In some example like this one. Determinant of this one, how we can find it? 4 times 3 subtracted by 2 times 1. What you got? 10. What does that mean? It means that this guy is invertible because the determinant is not 0. And it scales area by a factor of A. Whatever you multiply by this number is going to scale everything by 10. another matrix. This guy is going to be 0. So it means that we cannot invert that. So it means that this guy is singular, or equal to collapses onto a space, or there is going to be onto a line, 0 area. It means that this is somehow useless, or at least we cannot have it right now. So imagine that we do have 3 by 3 determinant, and we would like to find that. So that would be a little bit more complicated. So please be careful. So we do have the 3 by 3 matrix. This is the 3 by 3 matrix, and I would like to find some kind of determinant. We do have a couple of ways. But first of all, let's talk about the strategy. We find the determinant of 3 by 3 of it's a matrix by expanding along any row or column. This reduces the 3 by 3 problem into 3 2 by 2. And we can find the determinant for each of them and find the final one. Imagine that I do have something like this. And the method that I'm going to use is going to expand along row 1. It means that I'm going to consider this row 1. After that, I'm going to use these signs, positive, negative. I will tell you how we can use it. So when I do have the row 1, it means that I'm going to start from each entry. If I do have this entry, I'm going to put a law. Whatever row that I do have beside of this guy, and whatever column that I have beside of this guy are going to be vanished. Then what you have left, you have a matrix, which is 2 by 2, and we know how we can find it. Right now, find the matrix, or find the determination of that guy. In the meantime, you have to multiply it by A. With what sign? With the positive sign. So it would be A times, A is just a number, right? Entry is just a number. Determinant of E, F, H, I, whatever is that, E times I subtracted by F times H is going to give me a number. Then I'm going to do the same concept. Let me just get rid of this part. The same concept with the second entry of the first row, this guy. Still going to say that whatever that I have in a row are going to be vanished. Whatever number that I have beside in my column are going to be vanished. Finally, I'm going to have something like this. I do have the matrix that it has D and G and F and I. So I'm going to do what? I'm going to multiply by B, but in the meantime, I do have negative sign. So I do have subtraction, or by B times the determinant of this one. Finally, I'm going to do the same thing with the final guy. It means that I'm going to vanish everything that was here in the same row, vanish everything that was here in the same column, and use it for this determinant. I do have C multiplied by determinant of this guy, and that's going to be my determinant for this 3 by 3. So let's see another some concept. Let's see some kind of another way. At this point, I still showed you that how we can do that. Still the same concept that we did before. So let's just not focus on that part anymore. So let's work an example. See that how actually we can use that, but this time I'm going to use another column or another row, because at this point you see we can have 9 different ways in order to answer our example. And it doesn't matter which way you use, at the end of the day, your determinant should be the same. Imagine that I do have this one as my A, 520, 131, 410. And I'm trying to find a column that is going to give me the least amount of effort in order to find the determinant. As I just told you, any row or any column is acceptable. So what is the simple column over here? Apparently is this guy, right? So I'm going to choose this one, and I'm going to expand the whole thing based on that. But I should remember this guy, positive, negative, we'll consider that. Okay, it means that I have to consider the 0. Whatever that I have over here collapses, and this guy would remain. 0, which is going to be the first one, times the determinant of 1, 3, 4, 1, like this. So when I do have this 0, I don't care what is the determinant over here. That's why I choose this column. So everything is going to be 0. Simple. Next, I do have 1 as my next member. So whatever that I had over here is going to be vanished. What remains part is going to be your new determinant, that I do have it as 5 and 4, 2 and 1. It's going to be like this. This determinant is important because 1 is not 0 anymore, but in the same time, I still have to make sure that it's going to consider this negative sign because it was there as I just told you. Again, remember that. Positive, negative 1, or 1 with the sign of negative, determinant of 5, 2, and 4, 1. Find whatever number is that and you're good. And you don't even have to think about the final one. Why? Because you already have 0. So it doesn't matter what kind of determinant you use. At all time, you're going to have 0. So that one is going to be 3. I dare you to choose 2 or 3 other methods in order to find the solution. It means that choose whatever your row or column you would like. You use the expanding method and find the determinant again. At all of those ways, the final answer for your determinant should still be 3, and this is the beauty of the matrix of 3 by 3. So we all learned that, right? Let's see it in action. Let's see how we can use it actually. If you guys remember, I told you that somehow we can use it in our very question, 2 equations, 2 unknowns. I'm going to use that. So let's see. When you do have a problem like this, obviously the 2 ways that we already know is about elimination and substitution. What was the substitution? Means that you can some kind of write down one some kind of variable based on another one. What was elimination means? Elimination means that you have to do add and subtracts by respecting to the fact that one of this one should be multiplied by a number in order to eliminate one of the variables and some kind of final variable. So what would happen if you would like to try to use another way? We try to use the matrix way. So I'm going to show you how. The very first thing that you have to do is you have to write down the whole thing like the matrix. What does that mean? It means that the coefficients that you have, first of all, make sure that your some kind of variables are going to be aligned like this with also considering your results. I do have 2, 1 as my first row, 3, 4, second row. Multiplied by what? Multiplied by your variables. We do have x and y. Final answer should be 5 and 10. So can we do that? Yes, 2 by 2, 2 by 1, and we know the final answer is 2 by 1. So there's no issue, right? So I do have 3 matrices. I do have 3 matrices. A, coefficients, x, my variables, and b is the answer. How I can find that? So if I can find a way to move a to this side and multiply it by b, I finally can find x. How we can do that? By inverse. Somehow it's like this. 1 divided by a is going to be a inverse. We know it, right? Because a inverse times a is going to be 1 or identity matrix. Is that so? Okay, let's... The very first thing that I have to do means that define it. Define how I can move this one to this side. As we all know, based on some kind of rule of division or whatever you know, the first thing that we have to do in order to get rid of that is we have to multiply a negative 1 or a inverse by the whole concept, and we have to do the same thing by another side. Why? Because if I do that, I can actually write it down like this. A to the power negative 1 or a inverse times a is going to be identity, and x is still the same. Identity times x is going to be still the x, but on another side I do have a inverse times b. What? I have to make sure that I'm going to check one thing, finding the determinant. Finding the determinant means that my guy is going to be invertible or not. Why I do have that? Because one way, or some kind of the important way in order to find the one inverse, is to use this rule or this law. That's why the determinant is important. If I do have the determinant of 0, I'm going to have 1 over 0. It's completely undefined. So let's see what is happening. The definition of A inverse is that 1 divided by determinant of A. What was A? Was the guy that we used to have. This one, 2, 1, 0, 4. Times by a new matrix. That this new matrix has 2 parts that actually changed. The B and C were changed their position, and they were multiplied by what? I'm sorry. The B and C are just multiplied by negative 1, and diagonal section, they just change their position. It means that the normal matrix was A, B, C, D, and I believe you can spot the difference. A and D change their position. We do have D and A, and B and C just multiplied by negative 1. This is a rule, okay? You don't have to know why because it has a very advanced mathematical proof. This is just a rule. We memorize it, we used it, okay? So, and that's I can find the inverse. Let's just talk about this example. The determinant of A is going to be 2 times 4 subtracted by 3 times 1. Is that so? So, it's going to be 5. It means that 1 over 5 times my some kind of A and D should change their position. 2 and 4 should change their position. 3 and 1 should be multiplied by -1. So finally, I have to find this value. Whatever this value is going to give me a matrix which is going to have 2 rows, 1 column, and it's going to be x and y. If you just do this multiplication, in the meantime, make sure you also have to multiply by 5 and 10, right? It means that just before finding the 1/5 by this guy, it would be better to find this multiplication first and then do that. You still can find this one first and after that do that, it doesn't matter. And the final part, you're going to have 2 and 1. So x and y is going to be your 2 and 1. So you have to check it in order to make sure that you already have the right answer again. So guys, be very careful. Right now, we learned 3 important ways in order to solve the answer of 2 equations, 2 unknowns. The very first one was about the substitution. It means that find one variable, place in another, put it inside another equation, find that specific variable, and use it in another equation to find that variable. Another way was about elimination. Find a way in order to, when you add those two, some kind of equation together, one of your variables could be eliminated by doing some kind of changes while keeping the balance. And the final way was about using this method, which is going to be as the matrices itself, which right now give you enough toolkit in order to solve any kind of question that you have, if you are sure that you are going to have an answer for that one actually. So the part 2 is going to be the power of Gaussian elimination. So this part is important. So let me just talk about it and what is that, and then we are going to use it for 3 equations, 3 unknowns. We already know some ways in order to do that, but I'm going to talk about the way that I mentioned in the previous section, and I told you I will talk about it over here. So please be careful about this one. Be some kind of focus over this one. It's going to be a little bit complicated. So what is a concept? A robust method that we have for any size system. By the way, this work is going to be for any size system. 3 equations, 3 equations, 4 unknowns, or any kind of relation. Even the 2 equations, 2 unknowns is going to be acceptable. What is the goal? We are going to use the row operations to transform the augmented matrix into an upper triangular form. You guys remember about the triangular form, right? The upper one means that we do have a triangle that in its diagonal, we do have something in diagonal part, it could be anything, but on the top, everything is something rather than 0, but on the bottom, everything is 0. This we are going to solve using back substitution. So it means that the tools that we have, we can swap the rows. The rows means that just changing the position of this equation. We are not going to do anything, just swapping the rows. Multiply a row by a non-zero scalar. It means that you can, just like the way we did, you can multiply everything over here by 2, and you have to make sure this guy is going to be 2. We are not going to do anything. Add a multiple of one row to another row. What does that mean? It means that you can, for instance, add the first row and the second row and move it to what? To a specific concept or to a specific row. We still can do that. We are going to have a new equation. Again, we are not losing balance. So let's see an example. Imagine that I do have something like this, and I'm going to prove my word that I can use the 3 by 3. So what is that? X plus y plus z is equals to 6. 1, 1, 1 coefficients. 2x minus y plus z is equals to 3. 2 minus 1, 1 is equals to b. Is there some kind of coefficient? X plus 2y minus z is equals to 2. 1, 2, 1 is going to be the final answer. So finally, I can write it down like this. This is going to be my A. This is going to be my answer. So how I'm going to set up the augmented matrix? Something like this. I'm going to have my coefficients beside another column, which is going to be my answer. And I'm going to use a line between them. Why I choose that line? Because I'm going to separate my coefficients and answer. So let's talk about it. What should I do? I have to find a way or ways in order to convert this guy to something like this. Okay, that is important. Let's see how I can do that. Okay, guys, let me just explain this one to you because obviously you have no idea, at least right now, what's going on, and then talk about it a little bit more to some kind of try to reduce all of the confusion that you have related to this one, because again, this part is a little bit challenging. Okay, so I have something like this, and right now I would like to find a way in order to reach to the thing that I just told you. It means that by elimination, step by step. Okay. The first thing that I can do is operation number 1. I'm going to skip the R2, subtract it by 2R1, and use it in R2 itself. It means that whatever that I had in row 2, I'm going to change it with something. What is that something? That is row 2 subtracted by 2 times row 1. It means that whatever that I had in row 2, what was it? Well, anyway, it was 2, negative 1, 1, and I would like to subtract it by 2r1. I will tell you why. So I'm going to multiply everything over here by 2, subtract it by the r2, and replace it instead of that. Again, I'm not doing anything new. I'm just changing one equation with another equation. I still can do that, right? I can combine these three to find the fourth equation, fifth equation, whatever equation that I like, the way that we did before, right? So I'm going to do that, and the final answer is going to be something like this. 1, 1, 0, negative 3, negative 1, 9, negative 9, 1, 2, negative 1, and 2. So what I did, I just convert the second row to part of my upper triangular. So right now, I do have this one as 0. The second step would be something like this. I have to find a way in order to get rid of these two. How I can do that? Probably it still can do something with row number 1. Because as the way that you can see, if I can multiply this guy by 2, would be what? Yeah, we still can do something with that. Let's see what's going on. So at this point, instead of just using the row number 1, instead of just keep everything as the way it was, I'm going to still use the row number 1. So what should happen? Still, I'm going to do the same thing. The new row number 2 that I already have is going to be converted to another number 2. So my row number 2 is going to be converted to row number 2, which is a new one, subtracted by the previous one. If you do that, you're going to face something like this. 1, 1, 6, and we are going to do that. If you do that, you're going to face something like this. Let me get rid of that. As I told you, it's going to be a little bit complicated. So if you do that, you're going to have something like this. We are going to use that for what? We are going to use that to find a way in order to replace the row number 3. So row number 3, the new one, could be the R3 subtracted by R1. So I'm going to have something like this if you do the calculation. Again, operation number 4 is going to be simplify the R2. So what would happen if I would like to simplify the R2? It means that I do have negative 9, I do have negative 1, I do have negative 3. So right now, it's a little bit too much for me. I would like to get rid of that. Apparently, negative 3 and negative 9, they do have the same factor, it's negative 3. But by negative 1, I can just divide everything by negative 3 itself, right? So negative 3 divided by negative 3, it would be 1. Negative 1 divided by negative 3, 1 over 3. Negative 9 by negative 3 is going to be this one. So I do have this guy. And it means that something is good, because in the same time, I just simplify everything that was related to R2 itself. But also, I found a way in the previous part that I just did everything as I just told you, like this, in order to what? In order to get rid of the third part, which is going to be the second number itself. So in the meantime, I do have this one. And also for the operation number 5 is going to be the final operation. I'm going to simplify what's R3 to make it as the way it was, as the way that I like actually. What does that mean? It means that I have to make everything diagonal or make everything as 1. So I had 1 and I'm going to multiply everything by negative 3 over 7 because I would like to make it as 1 itself, right? Negative 7 over 3. Multiplied by what number is going to be 1? Obviously, it's going to be by negative 3 over 7. Negative by positive, and this guy multiplied by this guy is going to be 1. So if I do that, what am I going to have? I'm going to have something like this. Out of everything, I found this one. So am I done? No. Because right now, I just found my final variable, which was z. Z equals to 3. That's a fact. Right now, I have two other equations. Y plus half of z is equals to 3. Since I do have z, I can find y simply. And then I do have x plus y plus z is equal to 6. Since I do have y and z, I can find my y itself as simple as that. Guys, I know this way is a little bit complicated, but it's the way that you can solve 3 equations by 3 unknowns if you don't like to use the same, if you don't like to use the previous ways. Try to pause the video, try to think about it, try to do again the elimination. Again, we don't have only one way to reach to the fact of that we do have the diagonal and it's going to be upper triangle. We could have multiple ways. Try to find that way. Again, if you have any problem, try to comment down below. I will for sure make another video for you related to 3 by 3 in order to have a couple of more examples, because as I just told you, this guy is complicated, maybe by the concept, but most probably by some kind of the calculations, because you have to make sure you don't have any issue at the final day. If you want to double check, you have to do that. Find your x by z, put it inside your equation to make sure that all of them are going to be accepted. So, what did we just learn? We just learned what is happening in our world of, or the world of matrices. We have numbers that are going to be used in algebra, and instead of just normal algebraic unit like 1, 2, 3 or any other kind of expression, they're going to be inside a dimensional unit, and that dimension has rows and columns. Based on that rows and columns, we can decide that can we actually multiply those two matrices together, can we add them or subtract them. We just learned how we can use it in equations. Ax is equals to b. We learned about A inverse. We learned about the determinants and how we can find a specific thing. Why is that valuable? How we can use the matrices in 2 by 2 or 3 by 3. So again, try to rewatch the video to completely understand everything you saw. Still, if you had any problem, please comment down below. If I could, I would try to help you as much as possible. If I couldn't, I probably am going to make another video. So wait for the next chapter. We are going to advance topic related to matrices, that how actually we can use it in the real world. And without further ado, don't forget, by the way, to some kind of like and share and comment. It would be really helpful for me. My name is Mahmoud Kiasari. Thanks for being here with me. Have yourself a great day, night, whatever. See you around.